Okay, dear students, this is our fifth part of units and measurements. Okay, so you got some ideas about units and measurements. The last class we discussed about the dimensional analysis and dimensions. And now we are going to discuss about some new topics. This is not familiar to you. This is a new topic, significant figure. It is very important topic because you want to use this in chemistry also. Okay, significant figures. So, by the definition, a significant figure are normally those digits in measured quantity which are non-reliably or about which we have confidence in our measurement plus one additional digit that is uncertain. If we are measuring a value, I measured a value is 26.76. So, I am sure about the value 26.7, but I am not sure it is 6 or 7 something, the last digit. So, that last digit is called uncertain value. So, that reliable value, that is 26.7, that is reliable. Again, 16 is there, that is not reliable. So, including this value, we consider that are significant one. So, one reliable digit plus the last uncertain digits are called significant figure. So, by the definition, the significant figures are normally those digits in a measured quantity which are non-reliably or about which we have confidence in our measurement plus one additional digit that is uncertain. So, that last digit is called uncertain digit because I am not sure about that digit. That's why it is called uncertain. Okay. So, the larger the number of significance figure in the measurement, the higher is the accuracy of the measurement. If the significant figure increases, means the number of digit increases, the accuracy also increases. Okay, the larger the significant figure, the higher the accuracy that we can say. Okay, and suppose we can consider an example. Suppose the time period of a simple pendulum is 1.62. So, here 1 and 6 are reliable 1 and 6, while the digit 2 is uncertain. Okay, so this indicates that this 1.62 have three significant figures. 1.62 there has three significant figures. Okay, and again one more example. I measured the length as 273.6 centimeter. Here 273 are reliable, but that 6 is not reliable. It is called uncertain. Here we have 4 significant figures. Okay, in this case there are 4 significant figures. There are some certain rules for determining the significant figures. Okay, we have some rules to find the significant figures. So that we want to consider. What are the rules? The first one, all non-zero digits are significant. Very clear. All non-zero digits are significant. If a number, if we consider number 1, 5, 6, 7, so there are all the numbers are significant because there are no that numbers are non-zero one. Okay. For example, 13.75. So there is 4 significant figures. There is 4 significant figures. So that is the first rule. All non-zero digits are significant. And the second rule, all zeros between two non-zero digits are significant. If a zero comes between two non-zero digits, say example 100.05. So this zeros between 1 and 5. 1 and 5 are non-zero digits. So this zeros also significance. That means there is 5 significant figures. 100.05. So there is 5 significant figures. So the second rule is all zeros between two non-zero digits are significant. Okay, clear? Okay, now the third rule. All zeros to the right of a non-zero digit but to the left of decimal point are not significant. Means we can consider an example 86400. Here 8, 6 and 4 are non-zero digit but 00 are 0 digits. So here these 3 digits are only significant. That is the rule. Okay. So 86400, there is only 3 significant figures. But one more thing we want to remember, that is that zeros also may be significant if we obtain this value from an actual measurement. Okay, this comes from an actual measurement. For example, it is 86400 second. So it comes from an actual measurement. So we can say that there is 5 significant figures. Okay, then the next one. The fourth one. All zeros to the right of a non-zero digit but to the left of a decimal point are significant. Left of a decimal point are significant. If here there is a decimal point, so this number is also significant. Okay, so this is 648700 point. Point 0 is also there, then it is 7. So here we can consider that it is a significant figure of 6. So 846700 point consists of 6 significant figures. Or if there is another 0, then it is 7 significant figure. Okay, likewise. So all zeros to the right of a non-zero digit but to the left of a decimal point are significant. Clear? Then the fifth point. All zeros to the right of a decimal point are significant. So 161 centimeter is equal to 161.0 centimeter. Both are same but the significant figures are different. 161 there consists of 3 significant figures. 161.0 there consists of 4 significant figures. Then 161.00 that consists of 5 significant figures. After decimal point there is a 0, then that 0 is also considered to be significant. Okay, after decimal point, if there is a 0, that 0 is also considered to be significant. Clear? So that is the fifth point. And the sixth one. All zeros to the right of a decimal point but to the left of a non-zero digit are not significant. Means if a number is less than 1, so we can write it as 0.161 centimeter. This 0 is not significant. So there is only 3 significant figures. Likewise, 0.0161. There are 2 zeros to the left of that number. So that 0 is also not significant. So here also the significant figures are 3. Okay, clear? So 0.0161 consists of 3 significant figures only. Okay, and the next one. The number of significant figures do not depends on the system of unit. That is not depends on the system of units. If it is 16.4 centimeter, then it is 0.164 meter, and here 0.000164 kilometer. But all these have 164 are significant. So there is only 3 significant figures. Clear? If we are writing something in a scientific notation also, we don't want to consider that scientific notation, we want to consider that number only. Okay, so that number only we want to consider, and we can consider the net numbers if there is some non-zero or zero elements will be there. So that significant figures only we want to consider. We don't want to consider that powers, means we don't want to consider 10 raised to what. Okay, so if we are representing something in a scientific notation, we don't want to consider that power of 10. We are only need to consider that number. Okay, clear? Then rules for rounding of measurements. Sometimes we want to round the numbers after some decimal points. Okay, there are some rules for that. What are the rules that we want to find? Okay, the first one, if the digit to be rounded is smaller than 5, then the preceding digit is left unchanged. For example, we have a digit 1.4544. So I want to round it to be 2. So that 2 fours can be neglected and the last digit is 5 itself. Okay, that's an example. So if the number is smaller than 5, then the preceding digit is left unchanged. Means there is no change in that preceding digit. And if the digit to be dropped is greater than 5, if it is a 6, say 1.76, I want to round it to be one digit, so 1.76 can be rounded as 1.8. Okay, 1.8. Then if the digit to be dropped is 5 followed by a non-zero digit, then the preceding digit is increased by 1. Okay, if the digit to be dropped is 5 followed by a non-zero digit, and then the preceding digit is increased by 1. So we want to increase that digit by 1. Okay, then next one. If the digit to be dropped is 5, if it is 5, then the preceding digit is left unchanged if that number is even. If the number is even, then there is no need of changing that number or increase that number. If it is odd, we want to add a 1 to that number. Okay, that are the rules for rounding of a measurement. Okay, so consider these rules when we are going to round some numbers. Okay, clear? Then arithmetic operations with the significant figures. Arithmetic operations with the significant figures. So we can consider the things. The first one, significant figures in the sum or difference of two numbers. In the case of sum of difference of two numbers, we want to consider what are the number of digits after the decimal point. So the result also consists of that least number of decimal points. For example, if I consider a number 76.436 plus 12.5, so the answer is 88.936, but it want to be changed as 88.9 because the 12.5 consists of only one decimal place. Okay, there is only one decimal place. That's why the number is changed into 88.9. Likewise, 8.624 minus 3.1726. So answer is 5.4514. But it want to be rounded into 3 decimal places because the least number is 3 decimal place. So that is the answer is 5.451. So the rule is, in addition or subtraction, the final result should be reported to the same number of decimal places as that of the original number with minimum number of decimal places. Clear? We want to round the result with the minimum number of decimal places if something in that measurements. Okay, clear? That is the rule for addition and the subtraction. And in the case of a multiplication or division, in the case of multiplication or division, we want to change that number, means result, by the least number of significant figures in the multiplant or in the measurements. So in multiplication or division, the final result should be reported the same number of significant figures as that of the original number with minimum number of significant figure. Okay, for example, 53.2021, 53, two significant figure. 2.021, there is 4 significant figures. So the actual result is 107.113. So it consists of 6 significant figures. But here the least one is 53. So there is only 2 significant figures. So I want to round this as how? 2 significant figures. So I can write it as in the scientific notation form. Actually it is 1.07113 into 10 raised to 2, like that we can write. So I rounded it as 2 decimal points or 2 significant figures. So it is 1.1 because it is 7. Okay, I add that to the first digit. So that is 1.1 into 10 raised to 2. So that is here the significant figure is 2 itself. Okay, likewise. And another example, 3700 by 10.5. The result is 352.38. Here this number consists of 2 significant figures and it consists of 3 significant figures. But the resultant actually consists of 5 significant figures. So I want to write the result in 2 significant figures. So here we can write it as 3.52 in 38 into 10 raised to 2. But if I need only the 2 significant figures, I want to round it. Here 5, so here 2, 3 something. So 2 and 3 are less than 5. So I can round it as 3.5 itself. So the value is 3.5 into 10 raised to 2. So here 2 significant figure. Okay, clear. So the rule for product or quotient is in multiplication or division, the final result should be reported to the same number of significant figures as that of the original number with minimum number of significant figures. Okay, clear? Now we can move for the next topic. Accuracy and precision. What is accuracy? Accuracy means less error. We can say that less error. What is precision? Actually, precision is at what limit we are taking a reading or a measurement. That is considered to be precision. Okay. By using a scale, we can read 1 mm. Means that what is 1 mm is equal to 0.1 centimeter. Okay, likewise for a vernier caliper, we can measure 0.01 centimeter. So the precision increases 0.1 to 0.01. That limit is called the precision. So we can look. So accuracy. Every measurement is limited by reliability of the measuring instrument and the skill of the person making the measurement. Okay. Then if we repeat a particular measurement, we usually do not get precisely the same result as each result is subject to some experimental error. This is imperfection in measurement can be described in 2 ways. That is called the accuracy and the precision. So there may be some imperfections. If I am taking a reading and if anyone take a reading, there may be some differences. Each time if we are taking the reading, there should be some differences. Okay, so that consider accuracy and precision. So here accuracy, it refers to the closeness of a measurement to the true value of physical quantity. So if we are measuring something, we know the actual value, that is called the true value. If our measured value is very close to that true value, we can consider that our measured value is very accurate. Okay, we can consider our measured value is accurate if it is very close to that of true value. Okay, and it indicates that relative freedom from errors. So there is less errors. So as we reduce the errors, the measurement becomes more accurate. If the error becomes less, then the result should be accurate. Okay, so the accuracy means it is refers to the closeness of a measurement of true value of the physical quantity. Okay, how close the measured value to the true value or the actual value, that depends the accuracy. Clear? Then precision. Precision, it refers to the which resolution or limit to which the quantity is measured, that I already told. At which resolution or the limit to which the quantity is measured, that consists by the precision. So precision is determined by the least count of a measuring instruments. So I told about the meter scale and vernier scale. Here 0.1 is the least count of that meter scale. So least count is the smallest value that can be measured by using a measuring instrument. That is called a least count. So for the meter scale, the least count is 0.1. And that of the vernier, it is 0.01 centimeter. Okay, likewise. So precision determined by the least count of a measuring instruments. The smaller the least count, the greater the precision. The smaller the least count means when the number of points increases, the number should be precise. If it is 0.01, 0.1 is greater precision than 0.1. 0.001. So it is very greater that of 0.01. Okay, likewise, if the number of points increases, then the precision also increases. So the smaller the least count, greater is the precision. Okay, if we repeat a particular measurement of a quantity a number of times, then the precision refers to the closeness of the set of values so obtained. If we are repeating some experiments or we are taking some measurements, then the closeness of that set of values obtained refers the precision. So at that time, precision is the closeness. Okay. So we can consider some example. Three persons measured some weight. The actual value of that weight is, or the mass is 0.520. So there are the three persons A, B, C. The first person obtained the values of the first measurement 0.52 gram, second measurement 0.51 gram, and the third measurement 0.50 gram, and the average is 0.51. And the next one 0.516, 0.515, 0.514, the result is 0.515. And the third one 0.521, 0.520, 0.520, the result is 0.520. In the first case, A, in the case of A, this is not precise or not accurate. Okay, because the actual value is 0.520. So in this case, the precision is also not accurate and the accuracy is also not. So it is not precise and not accurate. Okay, so neither very precise or not accurate. And in the second case, that is precise. Precision is there, but there is no accuracy. The data for the student B is not more precise as they vary slightly from one another, because the variation is only a small, but the average mass is not accurate. It varies slightly, so it is precise. We can consider that it is precise. And in the third case, the result is very close, so that is very accurate, and here the value is also very precise. So the resolution for A is 0.01 gram and that of B and C is 0.001 gram. Okay, so this is the accuracy and precision. So accuracy means how close a measured value to a true value. That shows the accuracy. And precision means at what resolution or limit if we are taking a measurement. That shows the precision. Okay, clear? Then next one, error. So accuracy means the closeness of a true value to the measured value. So there are some errors. That is, error is something, the true value minus measured value. That change is called the error. Okay, so every measurement is done with the help of some instruments. While taking the measurement, some uncertainty get introduced in the measurement. That uncertainty, that change is called error. That uncertainty is called error. So every measurement consists of some errors. Okay, so as a result, the measured value is always somewhat different from the actual or true value. Clear? So the measured value is always somewhat different from the actual or true value. There may be always a difference. Okay, so the error in the measurement is equal to the difference between the true value and the measured value of a quantity. That difference is called error. So error is equal to true value minus measured value. Okay, clear? So error is the difference between the true value and the measured value. That is called error. Okay, so an error gives the indication of limits within which the true value may lie. Okay, every measurement has an error. Every calculated value which is based on the measured value has an error. So every measurement consists of some type of uncertainty, that is called a error. Okay, so there are many different types of errors. We can consider some different types of errors. The first one, constant error. Constant error. That is, the constant error means which affected each observation by the same amount are called constant errors. So if we are measuring by using a measuring equipments, there are usually some error occurs. Means if there is a 0.1 centimeter error in a measuring scale, so each measurement consists of that type of errors. So that is called a constant error. So that type of error is called a constant error. Such errors are due to the faulty calibration of the scale of the measuring instruments. That is because of the calibration problem. Okay, calibration means we are adjusting the accuracy. So that is called the calibration. So if there is a 0, that there is a small change in that 0 means it is not calibrated. 0 should be in the position of 0 itself. Okay, if sometimes the scale, if we are using a scale, the edge may be damaged. At that case, the 0 goes. Okay, so if we are measuring by using that scale, there is a constant error will occur. Okay, that is because of the calibration problem. So such errors can be eliminated by measuring the same physical quantity by number of different methods or apparatus. So we can neglect or we can reduce that errors by measuring that quantity by using some other apparatus or some other methods. Okay, that is called constant error. So constant error is due to the which problem? Calibration problem of a device. It is constant. That error is constant. If you are measuring anything by using that instrument, there should be the same error. Okay, so that is called the constant error. And another one, systematic error. It may be a one direction error. The systematic error may be positive or a negative. It will occur only one direction. It either positive or either negative errors. Such errors are called the systematic errors. The errors which tends to occur in one direction, either positive or negative, are called the systematic error. So we can eliminate such errors once we know the rule which governs them. Okay, systematic error can be classified into some other division. The first one, we can consider that it is instrumental errors, because it is due to which that inbuilt defect of a measuring instrument. Inbuilt defect. Okay, so that occurring due to the default in that measuring equipment. So for example, if I consider a scale or any vernier scale, so the zero of the vernier scale may not coincide with the zero of the main scale. In a vernier scale that consists of two scales, one is main scale, another one is the vernier scale. Basically that two zeros should be coincided. If it is not coincided, then there should be, if I am going to measure anything by using that measuring instrument, there are some errors. That is because that imperfection in that measuring instrument. Okay, so this error can be determined or detected by measuring a physical quantity with two different instruments. So this may be avoided if we are measuring the same quantity by using 2 or 3 measuring instruments. So the same type, or by measuring the same physical quantity by two different methods. Okay, so it can be detected by using 2 or 3 measuring instruments or measuring methods. Okay, clear. Then next one, imperfection in experimental technique. Imperfection in experimental technique. So this error due to the limitation of the experimental arrangement. It is due to the imperfection due to the arrangement, experimental arrangement. We can consider an example. Error due to the radiation loss in calorimetric experiments. And error due to the buoyancy of air when we weight a body in air. If you are taking a weight measurement, there are some buoyancy effect due to that air. So there are some errors may occur. So such errors cannot be eliminated altogether, but necessary correction can be applied for them. Okay, calorimetric means if we are measuring the body temperature, what we are usually doing? We are putting our thermometer into our armpit. Actually, that body temperature is not correct. Okay, that is the experimental error. We can consider that is an experimental technique error. Okay, likewise. So, next one, personal error. This error arises due to the individual's bias. So, lack of proper settings of the apparatus or individual's carelessness. So, this is based on an individual. That is the personal error. So, it is because of the proper setting problem or the individual's carelessness, anything. Okay, or etc. We can consider that. So, for example, when an observer holds his head towards right while reading a scale, he introduces some error due to parallax. We already learned the parallax method. If we are changing our eyes, so there should be a parallax effect. So the reading should be changes. Okay, due to that, the result also changes. That is a perfection error. Okay, so that is the personal error that comes in the personal errors. So the next one, error due to external causes. Means external causes, any external effect like pressure, temperature, wind, etc. Okay, that's also called error due to the external causes. That's also a systematic error. For example, the expansion of a scale due to the increase in temperature. If the temperature increases, that scale also increases. So the result may change. There is a error likewise. So such errors can be easily detected and necessary correction may be made accordingly. This error can also be minimized by controlling the external conditions during the experimentation. We can control the external condition during the experiment. So we can reduce this external errors. Okay. So these are the three errors in the case of a systematic errors. And the next one, random errors. The name itself, this error occurs irregularly and randomly. That's why it is called random error. The errors which occurs irregularly and at random in magnitude and direction is called the random errors because it occurs randomly. So such errors occurs by chance and arise due to the slight variation in the attentiveness of the observer while taking the readings or because of slight variation in the experimental conditions. Basically, we can say that if we are doing an electrical experiment, the voltages may be varies. Due to that variation, there are some variation in our measurement also. That is the random error. Okay. So in this, if we can reduce this random errors by taking the arithmetic mean of this observations. Okay. And the next one, least count errors. This is due to the limitation imposed by the least count of the measuring instrument. Means it arises with that instrument itself due to the limitation of that least count. Least count is the smallest value. So by using an equipment, we can measure that up to that value only or from that value itself. 0.1 is the least count of the scale. If we are measuring a something by 0.05 ranges, so there is a error. Okay, we can't measure that one. So that is called the least count error. The smallest division on the scale of the measuring instrument is called the least count, that I already told. So example, a meter scale has a least count of 1 mm. Its readings are good only up to this value. So if we want to measure 0.5 mm or 0.05 centimeter, so there may be some errors. Okay, that is called the least count errors. Then next one, the cross-sectional errors or mistakes. These errors are due to neither carelessness nor person or due to improper adjustment of the apparatus. Okay, this errors due to either carelessness kondo അല്ലെങ്കിൽ of the person or due to improper adjustment or due to the improper adjustments of the apparatus. There we can't adjust. The corrections can be applied for gross error. No corrections can be applied for gross errors. Okay, so these are the errors. What are they? First one. What is the first one? This one. Constant error, systematic error. Systematic error having consists of instrument error, imperfection in experimental techniques, personal errors, then error due to external causes, then random error, then least count error, then gross error. These are the different types of errors. So least count errors are random errors. We can consider that least count error is also a random error, but within a limited size. That only comes within the limited size. They occur with both random and systematic errors. It comes under the systematic error also. Okay, least count error is a random error, also it is a systematic error. So the accuracy of a measurement is related to the systematic errors, but its precision is related to the random error. Accuracy related to systematic error, but the precision is related to random error, which includes the least count error also. Okay, it's clear, I think. Okay, our next topic, absolute error, relative error and a percentage error. This is the another classification of our errors. So before going to this, we want to know the mean value of our measurements. Basically, if we are measuring something, say if we are measuring a length of something, we can measure it many times. So if we don't know the actual value, we can take the arithmetic mean of that measured values. That is considered to be the mean value or the true value. Okay, the mean of that measurements. So that is the true value. The absolute error means the deviation from that true value or the mean value to the observed value. That is called the absolute error. Consider here. Normal or Gaussian law of random errors shows that the probability of occurring positive and negative errors is same. So the random error can be minimized by repeating measurements a large number of times. Okay, then the arithmetic mean of all measurements can be taken as the true value of the measured quantity. Okay, then consider A1, A2, A3, etc. up to AN be the n measured values of a physical quantity. Okay, then true value A is given by, true value of A is given by the arithmetic mean. That is the arithmetic mean, A bar, it also shows mean value or A mean, we can represent like that. So that is equal to A1 plus A2 plus A3 plus etc. plus AN by N. So that's equal to 1 by N into summation I equal to 1 to N AI. So consider this only, this part only. If you didn't understand this, leave it. Okay, it also means that I is equal to 1 to N. The same thing is here. 1 by N into, we can give I equal to 1. So A1 plus I equal to 2. A2 etc. up to AN. This only represented by using this symbol, summation, sigma symbol. Okay, so here the arithmetic mean is equal to A1 plus A2 plus A3 plus etc. up to AN divided by N. So this A mean is considered as the true value. Okay, so first one we can consider the absolute error. It is the magnitude of difference between the true value of the quantity measured and the individual measured values is called the absolute error. This is the deviation or difference between that mean value to any individual measurements. So likewise we can consider, the first value A1 is our first value. So the absolute error, so that means the absolute error, the first absolute error, that is absolute error is considered as the letter delta symbol. So capital delta symbol. So that is capital delta A1 is equal to A mean minus A1. And likewise the next one delta A2 is equal to A mean minus A2. And delta A3 equal to A mean minus A3. And delta AN equal to A mean minus AN. So this delta A1, delta A2, delta A3 and delta AN are called absolute errors of A. Okay, clear? So this is the absolute error is the deviation from the mean value to the measured value. And mean of the absolute error or mean absolute error or final absolute error, it is nothing but the mean of the positive magnitudes of all absolute errors. If we are taking the mean of these absolute errors, then it is called a mean absolute error. That is represented by like this. Represented like this. So that is delta A mean. That's represented by delta A mean. So that is delta A mean is equal to delta A1. Modulus of delta A1. Modulus means we are only considering the positive value. If it is negative also we didn't consider. The positive only we are taking. So if it is a minus 1, we will take it as 1. If it is minus 0.5, we will take it as 0.05 or 0.5 likewise. So that it is delta A mean equal to delta A1 plus delta A2 plus delta A3 plus etc. plus delta AN by N. So that is the delta A mean, means mean absolute error. That is the mean absolute error. Or we can represent it as 1 by N into summation I equal to 1 to N AI. Okay. So next one, the relative error. It is nothing but the ratio of mean absolute error to the mean value. Mean absolute error to the mean value. So the relative error, it is the ratio of mean absolute error to the mean value of the measured quantity is called relative error. So relative error is equal to delta A mean divided by A mean. Clear? Then percentage error. It is nothing but if we are representing the relative error in percentage, then it is called a percentage error. So that is this delta A mean by A mean into 100. Then it is called percentage error and it is denoted as delta A. Clear? Absolute error, mean absolute error, relative error and a percentage error. Mean absolute error means the deviation from the mean value to the measured values. It is represented as capital delta. And mean absolute error, it is the mean of absolute errors. Mean of the absolute errors. And relative error means the ratio of mean absolute error to the mean value. If the relative error is represented in percentage, then it is called a percentage error. Clear?